Global sea levels are rising faster than historical projections, directly threatening the dense coastal megacities that currently house hundreds of millions of people. For centuries, civil engineering has relied on a single strategy for water management: static resistance. The goal is to build a solid wall higher than the projected flood level. This approach requires massive, rigid infrastructure. Nations invest billions of euros into systems of polders, deep-rooted dikes, and computer-operated storm surge barriers to artificially separate dry land from the sea. The Thames Barrier in London relies on 10 steel gates, each rising from the riverbed to form a physical blockade against incoming tidal surges. In the Netherlands, the Maesland Barrier protects Rotterdam with two 240-meter curved retaining walls, built to withstand the immense force of a North Sea storm. These static systems share a structural vulnerability. Their heights and tolerances are calibrated to historical weather models and past averages, rather than the dynamic, accelerating reality of current climate data. Current projections suggest global sea levels could rise by 1 to 3 meters by the end of the century. A rigid wall cannot adapt once the water surpasses its design height. Relying on fixed barriers against high-end flood projections creates a high risk of catastrophic failure, requiring a structural shift in how we engineer urban coastlines. Urban planners are now looking toward dynamic adaptation. This schematic demonstrates how buoyancy solves the elevation problem. Utilizing a floating foundation decouples a structure's vertical elevation from the mean sea level. The platform rises in sync with the water. Applying this at a civic scale requires converting basic displacement physics into high-load civil engineering, capable of supporting permanent, heavy infrastructure. Amsterdam's Eiberg district serves as a working prototype. Here, dense, multi-level homes sit directly on the water, aligned closely to mimic traditional terrestrial street grids. Engineers designed these as hybrid structures, combining the living standards of a traditional house with a shipyard-built foundation anchored permanently in place. The central architectural challenge is engineering stability. Planners must maintain equilibrium and deliver reliable municipal services to high-density buildings sitting on a substrate that is constantly in motion. The stability of a floating structure depends on Archimedes' principle. An object in water is buoyed up by a force equal to the weight of the fluid it displaces. This model illustrates the precise water volume a foundation must displace, calculating the exact metric tonnage of structural load it supports. To achieve this, builders replace traditional foundations with large, airtight concrete tubs. Shaped into a hollow basin, the concrete displaces enough water to float. Once afloat, the engineering challenge shifts to load distribution. If a dense bathroom module is placed off-center, the uneven weight causes the platform to tilt. Architects counter this through variable thickness casting, designing the tub to be thicker on the opposite side to perfectly offset weight. If a resident introduces a new heavy load to one side, the platform tilts again. Engineers correct this by installing modular, air-filled cylinders underneath the submerged heavy side, pushing that corner back up to restore balance. The floating foundation functions as a highly calibrated dynamic counterweight system, maintaining a level center of gravity regardless of internal weight distribution. Managing internal weight is only half the equation. The structure must also handle external kinetic forces from tides, currents, and weather. This diagram details the deep water mooring system. The floating platform connects to fixed steel poles using sliding ring brackets, locking horizontal position while allowing vertical travel. Driven 16 meters into the lakebed, the poles allow the entire house to slide smoothly with the shifting tide. Connecting a moving building to rigid utilities is a physical challenge. Standard pipes would shear under tidal stress. The solution is umbilical engineering. Power, sewage, and water lines route through flexible tubes inside connecting jetties, expanding and contracting like accordions to absorb the displacement. This creates a flexible, plug-and-play grid that anchors the floating community directly into the mainland's established infrastructure. By isolating the lateral forces and absorbing the vertical motion, the engineering makes the movement of the marine environment imperceptible to the residents living inside. While single-family floating homes prove the mechanics, they lack the raw density required to relieve overcrowding in major urban centers. Expanding this concept to a citywide scale requires pushing the engineering upward into high-density, mid-rise floating towers. Increasing verticality on water necessitates a shift in material science. Heavy structural steel creates top-heavy loads that could capsize a floating foundation. This schematic of an 8-story floating office shows the required buildup. Instead of steel, upper floors rely on cross-laminated timber to reduce weight. To prevent tipping, the concrete foundation is widened significantly, distributing the wind's kinetic energy across the water to lock the tower upright. By balancing displacement with lightweight structural materials, architects can replicate the high-density living configurations of standard land-based districts. Buoyancy physics and advanced timber engineering make it feasible to meet the vertical density demands of modern urban expansion without relying on solid ground. Connecting these individual mid-rise platforms together forms a macro-level urban grid, a blue city. This view visualizes the primary advantage of a floating grid: spatial modularity. Unlike rigid terrestrial blocks, floating schools, residential zones, or commercial districts can be physically detached, relocated, and reconnected to optimize the city's layout. Beyond flexibility, floating cities can operate as efficient, self-sustaining thermodynamic loops. The volume of surface water beneath the foundations acts as a natural heat sink. By circulating that water through the structures, the buildings passively regulate their internal temperatures. This continuous passive cooling, combined with localized solar arrays, reduces a district's energy consumption by 25% compared to conventional land-based infrastructure. The timeline to deploy these systems is accelerating. More than 200 million people are projected to live in areas directly threatened by rising sea levels. For many coastal megacities, building massive static defense grids like the Thames Barrier is an economic impossibility. Floating platforms offer a highly scalable alternative. They bypass the need for endless seawalls by adapting to the rising tide, rather than attempting to outbuild it. Urban planners are moving away from treating the ocean as a hostile force, instead viewing it as an adaptable structural foundation. For cities facing an encroaching ocean, infrastructure engineered to move with the water removes the primary failure point of coastal urbanization: the risk of being